To open up the subject of how probability forecasts are made, let's first look again at sensitivity to initial conditions. Remember, the sensitivity comes from the complexity of the climate system. And I'm going to represent this with a much simpler but still complex system, a pin table board game. If you're not familiar with this game, the idea is that you drop a metal ball down the funnel at the top and try to guess which compartment it will land in at the bottom. The ball collides with the many metal pins in the table, ricochets around in a complicated way, which makes it really impossible to predict into which of the compartments it will fall. It's a guessing game. It's a very complicated system, and it will serve as a simple analogy of the complicated interacting climate processes in the real system. In case you're finding it hard to imagine this game, here is a photo of a real pin table. It's placed on a slope, so balls launched, in this case by a spring device on the right, roll down the table with the pins complicating their journey to the bottom. This one has a complicated scoring system, but we're more interested in the pockets where the ball lands at the bottom. So let's do a seasonal forecasting experiment. We're going to drop two balls down the table. For the first, we imagine the table as the real climate system. And for the next ball, we imagine the table as our seasonal forecasting system. For the first ball, in real climate mode, the ball's journey represents how complexity can influence how the season ends up. In our analogy, we can consider the bins as climate events. Remember, either an event happens or it doesn't. Either a ball lands in a particular bin or it doesn't, it lands in some other bin. So we have well-defined events. Keeping with our analogy, let's assume this time the ball falls on the dry side of the table, where you can probably see it's going to fall in my cartoon. So a dry season is observed. Now it's time for the second ball. With the second ball, the table is going to represent our forecast model. As we are using exactly the same table as for the first ball, when we assume the table was the real climate system, it means in this representation our climate model is effectively perfect. So we are not considering model imperfections as a source of uncertainty in this example. So we travel back in time to before the season we are trying to forecast, the first drop of the ball. We observe as closely as we can the starting position of the first ball as it sat in the funnel for the first drop, because we have to get our initial conditions as accurate as we can. There won't be much error because the opening in the funnel is only slightly wider than the ball, but there will be some. We drop the ball, and what do we find? Well, even a very small difference in the starting point means the ball will strike the first pin differently and will depart in a different direction than the first ball did. And these small differences get amplified on its journey down the table as the ball interacts with a different set of pins than the first ball interacted with. Basically, because of complexity, a single drop of the ball is simply not predictable. Despite efforts to be as precise as we can with the initial conditions, if the ball lands in the same bin as the first ball, which means a perfect forecast of the dry event, it will be complete luck. So complexity and sensitivity to initial conditions, sometimes referred to as chaos or natural internal variability, hinder our capacity to make predictions. So what's to be done? Well, if we don't have a means of making a real forecast, we can at least observe the climatological probability of our events by counting how frequently it's happened in the past. And we discussed this in the previous section. Using the table in real-world mode, we could drop 100 balls down the table and count the frequency of landings in each bin or event, like so. Let's look at the extreme dry season event on the far right. Let's say 5 balls fall in that bin. what is the climatological frequency of that event? 5 out of 100 balls, yes, that's 5%. So the climatological frequency and probability of that event is 5%. This is useful information, but it's not a true forecast. And any further drop of the ball using the table in forecast mode for, say, a particular upcoming season is still unpredictable. Fortunately, initial conditions sensitivity, chaos, natural internal variability, is not the only factor operating. We have not considered yet the climate drivers introduced in Module 2.2. The sea surface temperature anomalies, or temperature differences from normal, are the most important climate driver for many regions of the world. The map shown here is for December 1997, and the warm sea surface temperatures of the strong El Niño in that year are highlighted. These anomalies are very large in geographical scale. They change slowly and persist for long periods of time, several months at least. They exchange heat with the atmosphere, and this sets up extensive changes in wind patterns, which in turn can affect average weather over a season in many parts of the world. Remember, the atmosphere is a relatively thin layer over the Earth, analogous to the skin on an apple, so the sea surface can impact the atmosphere relatively easily. The land surface can do so too. Sea surface temperatures are not the only climate driver. If you consult reference 1 of this module, you'll find information on other climate drivers. The influence of climate drivers is represented in our cartoon by a tilt on the pin table. The exact drop of an individual ball is still unpredictable, but it is clear that now the probability of the ball dropping on the dry side, the orange bars, is increased relative to climatology, the green bars. And the chance of the extreme dry event on the far right is now about 3 times the climate chance. In this cartoon, 15% rather than 5%. But there is still some chance, because of the complexity, that the ball will fall on the wet side. The cartoon should not be taken to suggest that El Niño always increases chances of dry. This will vary with region. The illustration here fits with the West Africa June-September season, for which El Niño does favour dry conditions. For other regions, such as Equatorial East Africa, in the October to December season, El Niño exerts an influence towards wetter than normal conditions. The pin table is a very simple analogy for how complex climate model ensemble systems are employed in seasonal forecasting. For each forecast, model predictions are made many times, each with slight variations in initial conditions, carefully designed to reflect the uncertainty. The collection of predictions is called an ensemble, and each individual prediction an ensemble member. Most systems have between 20 and 50 ensemble members. The prediction from each member is a valid possible outcome, derived from a realistic model, but it will be subject to initial condition uncertainty, so in general different members will predict different events. The range of different events predicted by the ensemble represents the uncertainty in the forecast resulting from the initial condition uncertainty. This is a bit like observing the distribution of the orange balls dropped through the pin table. The interactive ocean component in the model predicts the large-scale sea surface temperature influences, which change slowly and are less prone to chaos effects than the atmosphere. And these influences can enhance or diminish the probability of events. In the cartoon, they put a tilt on the pin table. And this allows us to estimate the change in the probability of events.